Good evening, everyone. My name is Linda Conlon. I'm the Chief Executive of the Centre for Life, and it's my very pleasant duty to welcome such a large gang of you here this evening. Lovely to see so many people. Those of you who visit the Centre for Life regularly, and I can see, despite these bright lights, quite a few familiar smiling faces. I think you know that we offer a lively programme of talks and events on a regular basis. And we've had some pretty well-known and interesting people come to talk to us. But this evening is a very special occasion. We are honoured to have a giant of science amongst us. Not only is he a Nobel laureate, but he's also a Geordie, born a mere stone's throw from the Centre for Life in Elswick. I'm truly delighted to welcome Professor Peter Higgs, who was awarded the Nobel Prize for Physics 3 years ago. Peter very, very rarely makes public appearances, and so this occasion is even more special. I'm sure you'll appreciate that Peter's career history is simply too long for me to read out this evening. Suffice to say, he's won numerous awards for science. He's been granted the freedom of several cities, including freedom of the city of Newcastle in 2014, and he has a string of honorary degrees. He's even been honoured by a brass plaque installed on Newcastle's quayside as part of the local Heroes Walk of Fame. But back to the Nobel Prize for Physics. I looked up the official definition of what it was awarded for. This is the public motivation, as the Nobel people call it, and this is what it actually said. The Nobel Prize was awarded for the theoretical discovery of a mechanism that contributes to our understanding of the origin of massive subatomic particles, and which recently was confirmed through the discovery of the predicted fundamental particle by the ATLAS and CMS experiments at CERN's Large Hadron Collider. Phew. Now, I'm sure that many of you in the audience understand all of that perfectly. And so, if you do, you can snooze through the next bit. But for those of us who need a little bit of help, I'm going to ask my very good friend, Graham Farmelo, who himself is a physicist, as well as an experienced science communicator and writer, to explain what it actually means in plain and simple language so that we can all understand it. So, ladies and gentlemen, please join with me in giving a very warm welcome to Nobel laureate Professor Peter Higgs in conversation with Graham Farmelo. Thank you.
Thank you, Linda, for that gracious introduction. It's great to be back in Newcastle, and in particular to be here at the greatest science centre that Britain has. We agree with that? Yeah. Not loud enough. Come on. Yes. Right. Come on. We should be proud of this place. It's a great place, and it's a real privilege for me to have an opportunity to give a bit of background to the great work that won our friend Peter Higgs very deservedly the Nobel Prize so recently. The first thing I want to say is that yes, we're here to talk about science tonight. We're also talking about one of the greatest cultural achievements of the human race in the 20th century. Make no apology for saying that. It is a truly colossal achievement, of which Peter Higgs's contribution is a very notable one. I'm talking about what's called the Standard Model. Only physicists could come up with a term so boring for something that is so important. The Standard Model. And what that model, better called theory, does is it gives a portmanteau, a broad description of the forces that govern the behaviour of atoms. Now, this was done in a remarkably short span of time. If you bear in mind how long human beings have been around on this earth, got up on their hind legs and walked around, this has only happened in about 100 years, that the human race went from debating whether atoms existed to actually having a theory of what goes on inside them. This is, friends, a colossal achievement. And I want to give you just a bit of background to justify what you may think is hyperbole when I say, when I praise the theory that we're talking about tonight. Let me just say straight away that this is the best theory, tested theory in science. Umpteen decimal places, tested over and over again, all over the world from different cultures. This is a theory that really is extremely robust. Despite the best efforts of thousands of experimenters at CERN at the moment, we find ourselves dotting I's and crossing T's. It's an incredibly good theory. And another important thing to get right, especially on a night like tonight when we're celebrating the work of a really great theoretician, is that the Standard Model is not the work of any one person. It's the work of hundreds, thousands, even tens of thousands of people. Yes, there are distinguished contributors, and Peter is one of the most distinguished, make no mistake. But science is about community. It's about people being part of a community that produces things. Yes, if Shakespeare had not lived, we would never have King Lear. If Jane Austen hadn't lived, we wouldn't have Pride and Prejudice. That's true. But in science, people are actually, right, if you don't do it, somebody else will, right? There's this feeling of knowledge that in science, it's a very competitive thing because people know that if you don't get to something first, somebody else will. And ultimately, it's the community that does science. It is not just the work of your Einsteins and what have you. So let me just say a bit about this Standard Model. It's based on two glorious foundations of physics, 20th century physics, two theoretical foundations that have so far proved absolutely rock solid. Now, the first one is due to a scientist that you may well have heard of, Albert Einstein. He presented the first completely coherent description of something we call the special theory of relativity, which is a modification of our common understanding of space and time. His paper that he wrote just out of his PhD is a classic because it shows that the picture of space and time that Newton and other tremendous scientists had needs a bit of tweaking in order to make it consistent. That was done in 1905. Now, that's a year notable in culture for the discovery of the special theory of relativity, and almost as important, the first time that Newcastle United won the First Division Championship in the 20th century. Move on, quite a bit of time, another 20-odd years, and you come up with actually a much more revolutionary theory. In fact, the most revolutionary theory that science has seen for decades. Nothing more revolutionary than this was produced in the whole 20th century, and that is the theory of quantum mechanics. Now, this is something that is really a break from the ordinary stuff that one learns, the scientists have been practicing for years, since the time of Newton and many other people, the study of motion of ordinary everyday particles. When you get down to the atomic and subatomic level, things change. You can't use those rules that Newton set out way back in his Principia. You have to change things in a way that had people, frankly, disbelieving. Its own, one of its creators, Max Planck, who wrote the first paper on this subject, went to his own funeral in a casket, not believing the interpretation of his work that we now have today. In other words, even he didn't see quite how revolutionary his own work was. So by 1927, that theory was bedding in, 22 years after Einstein, when we had a really solid quantum theory that described the motion of particles on that scale. By the way, that was the fourth time that Newcastle United won the championship. I think they've done it since, actually, but I'm sure time will tell. Now, the point is to apply those two things, special relativity and quantum mechanics, to these entities inside the atom. Those are the golden things that we have, the golden arms, so to speak, that we have. And they're applied by recognizing something that Newton actually knew nothing about. The modern physicist doesn't think in terms of particles moving around, but in terms of fields. We've all seen magnetic fields scattered around iron filings, for example, and we hear the word bandied around, gravitational field and what have you. The language of subatomic physics is of the field applied through quantum mechanics and special relativity. And it was one of Peter's predecessors, Paul Dirac, who was a great pioneer of that theory, and showed that because of quantum theory and relativity jammed together, that you actually predict that particles don't exist just in themselves, but have an antiparticle attached, associated with them. And this idea of antimatter came out of those two theories. So the Standard Model emerged. People debate this, but this theory of the weak electromagnetic and strong interactions that fashion the work of the atom first really came together in only the 1970s. Many of you will have been around then. It wasn't something that made instant headlines, but it gradually took shape around that time. And it's something that you could, in the time-honored way, put on in terms of its basic equations, not their interpretation, but the equations themselves. You could put it on a T-shirt. The Standard Model says that there's a handful of particles that make up matter, and another separate group of particles that mediate the forces between those particles. We don't need to talk in detail tonight. You can go and read it online. You can go read it in books if you're that old-fashioned. But you can go and read about the nature of those particles. But the key thing is that there is a theory that governs their interactions through something called a gauge theory, something of which Peter did his great work. Now, while theorists were doing this, it's extremely important to realize that there were experimenters constantly driving to push the theoreticians and explore in their own light what is going on in this peculiar subatomic world. And they use a technique that at first sight looks so crude as to be something you think should be dismissed. Namely, that they take these tiny little subatomic particles and smash them together at the highest possible energy and see what happens. Now, it's by that incredibly crude method, superficially, that it's the only, well, not the only way, but it's one of the very few ways in which you can probe what is going on at those very short distances and at very high energy. And it's data, observations from those experiments that can be tested by the Standard Model. Something that's perhaps a bit more concrete is that if you use that Standard Model, then it applies directly to when the energy of the universe was its highest, which was in the Big Bang, the very early stages of the universe. Then these particles were crashing together. This is 13.8 billion years ago, and through the insights of great theoreticians, we can use that theory to study what was going on 13.8 billion years ago. And if you want one thing, I think, that shows you the power of the human mind in this, you can take a bunch of what looks like hieroglyphics, these mathematical equations and symbols, and you can project it in the human mind back 13.8 billion years to look at the interactions that were going on right in the early moments of the universe. Now, that is an astounding thing to be doing, is it not? That's an incredible thing to be doing. And it's through the work of Peter and others that we've got to this position of having such a great theory that is now testable both in the particle accelerators and in terms of what our cosmologists and astronomer friends can test. One last thing I just wanted to say here. I stressed earlier that this Standard Model came together really in quite a short space of time, just over a century. A colossal achievement in science, as I've said. It began actually at the tail end of the 19th century, when the British physicist J.J. Thomson first discovered the first subatomic particle, in other words, a particle smaller than the atom, a constituent of every atom. Now, if you go back and look at the announcements that J.J. Thomson made, you'll see that several people wrote in writing they thought he was joking. They simply could not conceive that there could be things that were smaller than atoms. So to us these days, I think many people, we take that for granted. Not that long ago, people found it incredible that such a thing could exist. Now, you could have called that particle the Thomson particle, but we didn't. We called it the electron because that name existed beforehand. Thomson discovered the electron in a laboratory experiment that would have cost, if you make adjustment for inflation and what have you, a few £100. Now, you go to CERN, the giant Large Hadron Collider, you're talking about billions of pounds spread over a number of years in order to make these discoveries. But a much, much more powerful machine requiring tens of thousands of people to take the data and interpret it. If you come to the end, one should never say the end in science, but you come to when the last part of the standard model was put into place, well, that happened because there was one critical part of the standard model that I and many other people learned in graduate school that was untested. And that was the existence of a particle that I learnt about I've tried to think how many years ago, called the Higgs particle, sometimes called the Higgs Boson. This was in textbooks, we read about it. We thought, well, this is a bit difficult, but I suppose it makes some sense. But could it really be right? And we had to wait a long, long time, a huge investment of effort internationally from Britain, but from scientists all over the world to smash these protons together and see these incredibly rare events where there could be telltale signs that particle existed. One of the problems was that the theoreticians, even ones as clever as Peter, couldn't actually predict how heavy that particle was. Right? So we knew how it might fall apart, but we didn't know exactly where to find it. So this was a real challenge. In 2012, I was actually in Princeton in the where I was spending the summer that year. And word got about that there was going to be a big announcement from CERN. And the date was very memorable if you were in the States in particular, because it was July the 4th. And word had got about on social media and what have you, that maybe, just maybe, that the particle named after this gentleman here had shown up after all. This was the scene at CERN on July the 4th, 2012.
Sensitivities, if we combine the ZZ and gamma gamma, this is what we get. They line up extremely well, and in the region of 125 GeV, they combine to give us a combined significance of 5 standard deviations.
Higgs Boson. So will you welcome Peter Higgs? So Peter, do you remember that? That's not a silly question.
Yep, it's hard to forget.
Tell us your if you can remember your thinking when you heard that the particle that had come to be named after you had actually shown up in these experiments.
I think I should perhaps reveal that I knew what to expect the day before.
Live TV.
Well, CERN had prepared a not very clear, somewhat ambiguous press release because they didn't really know what the two teams were going to say.
Even the day before?
Well, they knew that it was going to be interesting, but the press release was a bit slightly non-committal, but indicated that it was going to be a discovery, but it wasn't quite clear. But because the CERN audiovisual department wanted to interview me about my reaction to this, I had to see a copy of that the day before. So I had some preparation. I knew that it was going to be quite an event, but I didn't know quite how much of an event it was going to be in terms of, the discovery at the level of 5 standard deviations, which was announced essentially by both of the experiments. So I had a bit of advanced warning, and so I was all prepared for something interesting to happen when I took my seat.
So you see how understated Peter is. I mean, because you'd been waiting for that for 50 years.
Well, pretty close to it. Yes, I mean, it was 1964 to 2012. So
yes. No, we don't want to go over the detailed history of this, but it's important, though, to say that in addition to your good self, the Belgian theoreticians François Englert and Robert Brout had come up roughly the same time with a similar idea, which you might just want to say a little bit about.
Yes, indeed. I mean, I should perhaps give you the flavour of how people did things and published things back in 1964. It was, I would say, almost before Tim Berners-Lee had been invented. There was no internet, so people did not publish advanced copies of their work online. There was no such thing to do to put it on. So it was very old-fashioned stuff. It was done by writing a paper and sending a copy off for publication to the appropriate journal, and at the same time distributing preprints to institutes that you knew about that had similar interests to your own. And it just happened that there were 3 groups of people independently working on the same kind of problem at the time. There was at the end of it all, when the American Physical Society awarded a prize, it went to 6 people, but there was a gang of 2 in Brussels, Robert Brout and François Englert. There was a gang of 1 in Edinburgh, that was me, and there was a gang of 3 at Imperial College. And it wasn't until the preprints, the versions of the Brussels paper and my paper got to Imperial College rather late at the beginning of October, that the people at Imperial knew that the others had got there first, as it were, because there'd been a postal strike. So the arrival had been delayed. So it was a situation which couldn't happen nowadays.
Yeah. Would you say, it's not a good question to ask someone of your modesty, but would you say that it created a sensation at the time, or was it something that was interested in a small group of people? What would you think? How would you characterise the reaction?
Well, I think I should perhaps quote the late Tom Kibble of Imperial College on that. He once said, our work was greeted with a deafening silence.
Good, that will do nicely. In the years, because we know this was 1964 when we were doing this. I might say, just to get a sense here, Alec Douglas Hume was, I was going to say, on the throne, but he might as well have been, actually, he was Prime Minister. And Beatles are just about to release A Hard Day's Night. So this is the time frame we're in. Right? You had roughly 50 years so then. Can you say candidly about your confidence that that particle would be discovered? Would you say that it was did it oscillate? Did it stay the same, or what? How would you say your own confidence?
In 1964, nobody had any idea what sort of mass it would have. There was nothing in the theory to indicate that, and all that can be said is that if it's not there, the theory is just a disaster.
Did anyone ever say that? Did anyone ever say that? That's quite a strong word.
Well, not in those words, but I mean, it was a situation where one was searching for a kind of theory from which everything could be calculated. But if you had a theory which, when you went beyond the crudest calculation to the quantum corrections which have to be added on to get a bit more accurate result, if you end up with predicting that the answer for something which you can measure is infinite, you know your theory is sick. Yeah. And it was like that. Okay. So it was actually not until later, the work of the Dutch theorists, that it was clear that everything was all right. But
may I characterise that? Please correct me if you that you were actually looking at a theory that people were aware was quite dodgy in terms of its because you couldn't calculate certain things in it. So you were not working with a robust theory, so to speak. Is that a fair statement?
Well, we were sort of finding our way to what might possibly work, and with the guidance of the very successful theory of quantum electrodynamics, which had gone before. And the important thing was that we managed to include the ingredients which made quantum electrodynamics work in a theory which could deal with the exchange of massive particles for the weak interactions as well. Yeah. But it wasn't clear at the beginning that was going to be possible. We were just doing our best, as it were.
It's true. I mean, you were saying that this quantum electrodynamics theory, which is the theory of electrons and photons and how they interact, after the Second World War, that had become something that come to some sort of fruition through great work of Feynman and Tominaga and Schwinger and Dyson and what have you. But what you and your colleagues were doing were trying to actually bring that under the same carapace as the weak force responsible for radioactivity as well. So you were doing something that was a bit more ambitious.
Yes, indeed. And the background for that was that I mean, previous attempts at a theory had been, as it were, fed in from the evidence, from the phenomenology, and when you took them seriously as a quantum field theory that you wanted to calculate with, they were clearly a disaster, and a lot of people had just given up on that one and gone and done other less ambitious things. Yeah. So we were actually in a rather minority in the theoretical community at the time.
Yeah, it's important to bear in mind. All right, let's just change tack, if I may, for a minute, and just bring you back to this great city we're in at the moment. You were born in Newcastle. How long were you here as a boy?
I think I'd left by the time I was 1 year old because my family moved to Birmingham.
Do you have fond memories?
So I have no memories earlier than the age of 2.5 in Birmingham.
Yeah, right. And then from Birmingham you went to
Bristol in wartime.
Right.
Yes.
Right. Okay. Now there you do, presumably, because that's where you were schooled, yes, in Bristol, yeah.
Yes, I mean most of my high school career was in Bristol. It started a year earlier on the outskirts of Birmingham, but then we moved to Bristol, and I went to Cottam School, which was one where Paul Dirac had been a pupil.
Can you say what? As you recall, because it's always difficult to say some years on, but can you give some sense of what led you to go from a young boy to somebody who wanted to do this very peculiar thing of being a theoretical physicist? You wanted to do that, obviously, when you went to university, but what stimulated you to do that, do you think?
It was a gradual process because my father was an electrical engineer who had spent all his working life with the BBC, and the reason I was born in Newcastle was that just after the BBC started up in about 1922 or something like that, they started setting up regional centres. My father was a new graduate of Bristol University and wanted a job. He had a background as an amateur radio enthusiast. So he got the offer of a job, and he was told it's in Newcastle. So that's why I was born in Newcastle, quite a number of years after he had moved up here. Mm-hmm. Mm-hmm. But well, that's the family background at least.
But in Bristol.
In Bristol,
yes, yeah.
When I moved to school there, to Cottam School. With a father who was an electrical engineer, I thought of myself possibly as a future engineer like my father. But I had also picked up some things about physics and mathematics from his bookshelf. For example, his student textbook on physics was the book on natural philosophy by Thomson and Tate, the two professors at Glasgow and Edinburgh University. And I picked up calculus from his mathematics books and so on. So I had some idea about other things than engineering, but when I started in school, I gradually realized I was not cut out to be an engineer. I wasn't really practical enough at home. It was my father who was the engineer who did all the sort of practical things. I got left out of that, so I never learned any practical skills. So I very rapidly began to think in terms of pure science. And because I was at Cottam School, clearly, it's clear looking back, I was influenced by the fact that when I stood at the back of the hall in the morning assembly, on the platform at the back of the platform was a board of names showing the honours gained by former pupils, and there was a name which occurred many times over, and that was Paul Dirac. And I began to be curious about who this guy was.
Even not knowing what Paul Dirac had done? Even though you didn't know what he'd done?
I didn't know what he'd done, but then, I mean, as I explored physics, and, in those days, good pupils got prizes on the basis of examinations and so on. And one of my prizes was certainly a book about the wonders of science, which told me about things which involved atoms and molecules, and that's where I first, located the name of Dirac again. So I began to get a feeling of what this was all about, and that it was interesting.
Yeah, well, just from what I know about Dirac, he went to, his father was teaching in that Cotham school briefly, right? Dirac's father.
Yes.
And he went to a school that was superseded by Cotham School, and he lived about a quarter of a mile from where you were being taught, and that's where he first heard about quantum mechanics, in his house there.
Yes. I in fact, I think was taught by one or two people who had taught Dirac. They were near retirement, of course.
Taught by Charles Dirac?
No.
Oh, I beg your pardon.
No. Other teachers. There was a man who taught physics named Willis.
Oh, yes.
His son, Danny, was a contemporary of Dirac's as a pupil there. Mm-hmm. Dan Willis was away in the armed forces in wartime, but his father was still teaching.
I see. Okay. All right. So when you went to university where?
I went to university at King's College London. Right. It was a bit accidental. In wartime, King's College London had been evacuated to Bristol. So I had met King's College students, particularly where I lived most of the time that I was at school, in a Victorian house divided into two flats, and in the upper flat was an engineering student at King's College. So I began to be aware of King's College. So when at the end of the war my family were reunited in London, my father had spent most of his years in Bedford, where there was no accommodation for family. I naturally took an interest in King's College as a place to go. I was more inclined, in fact, to go to University College, the godless college in Gower Street. But when I made contact with King's College and got an interview with the sub-dean of science in the year that I spent in school in London before becoming a university student, I got a very friendly welcome, and I got more response from King's College than University College, which was more bureaucratic. It was the way they dealt with applications. And this was a time when universities were filling up with ex-service people. A lot of people who were coming out of schools wanting to go to universities went and did their national service first. And so it was a tricky business deciding where to go. So when I got an offer from King's and I hadn't heard from UCL, I accepted it. And that's how I came to be there.
And you went on then to do a PhD. These, ladies and gentlemen, were the two papers, I hope Peter's not going to disagree with this, that basically were the papers that Peter wrote on his own, 27th of July 1964 and the 31st of August 1964. Now, what stage in your career were you at that stage, Peter?
In 1964, I'd been a lecturer in mathematical physics at the University of Edinburgh for 4 years, having completed a PhD at King's College in what was called molecular physics, because I was a physicist. Otherwise, it would have been identified as theoretical chemistry. It was quantum mechanics applied to molecules. And I was fortunate to pick up a prestigious studentship. It's called a senior studentship, awarded by the Royal Commission for the Exhibition of 1851, based on it was the successful exhibition out of the proceeds of which all the museums and Imperial College in South Kensington in London were created.
And Dirac as well, incidentally.
Yes, Dirac himself had held such an award previously. It enabled me, it was for 2 years. The first year was my final year before I wrote up my thesis. So I then had 1 year left, and I was able to use it with the permission of the people who'd awarded it to move to Edinburgh with my own money, as it were, so that I wasn't dependent on having money from the University of Edinburgh in order to work there. And that was how I first moved to Edinburgh for 2 years as a postdoc. January 55 to the end of September 56.
Right.
Then I failed to get a lectureship in Edinburgh, which was vacant, and ended up moving to London with an ICI fellowship where I wanted to work when he arrived with Abdus Salam at Imperial College.
Mm-hmm. So when you got to 1964 with these two papers that are now seen as classics, of course, I mean, each of them, I might say, ladies and gentlemen, about 1 page long. Not 50 pages, about 1 page. Now, it's good, but try and read them if you're not a specialist physicist. But they are remarkably, almost poetic in their concision. But Peter, when you wrote these papers here, where were you on the scale of this was a routine paper, I won't remember it, and I really think I've done something memorable there? Where were you on that scale?
Well, I had at the time a graduate student who had gone away to spend some time in Ankara with the theorist Faisal Gursi, and when he came back, he, according to his account of it, and we sort of exchanged news of what we'd done, I said, I've had my first real idea, the only idea I've ever had. I knew that I'd succeeded in doing something which was going to be important. I didn't know quite how it would fit into particle physics at that time.
I might say, I can't resist giving an Einstein anecdote in there. You've probably heard it. The poet Paul Valéry, the French poet, said to Einstein once, I think it was 1923, do you have a notebook to write down your ideas? And Einstein laughed and he said, I don't need one because I so rarely have an idea. It's true. But you're really saying that you thought it was a real idea. I mean, that's a real contribution.
Well, it was the culmination of several years being puzzled about a certain type of theory which had been started in 1960 by the Japanese-born theorist at Chicago, Yoichiro Nambu. And there was a debate in the theoretical physics literature about whether a certain difficulty in Nambu's program, which might apply to particle physics, whether a difficulty could be resolved. And one weekend I realized I knew how to do it. So
you sound funny. You sound confident there. I mean, we talked quite a bit about Dirac here, but he said when he wrote his famous equations, the famous Dirac equation for the behavior of the electron, that he was the first person to write down an equation where you could use quantum mechanics and relativity. And he said he was actually scared, right? Because he was so frightened that somebody might say, "Well, that's wrong," because of something. Did you not have any apprehension that somebody might think, "No, you've forgotten this or that"?
Well, in the early years, there were people who kept telling me I was wrong.
Oh. Do you have their names? You want to know? Really?
Well, my most terrifying experience came most of 2 years later when I was over the other side of the Atlantic. I'd published by... Well, I hadn't quite published. I'd produced the preprints and sent off for publication a longer paper, which spelt out in detail what I had said rather briefly in 1964. Yeah. And the distribution list for preprints from the University of North Carolina Institute of Field Physics, as it was called, included Princeton and Harvard, and the very positive response that I got to that preprint came from Freeman Dyson.
Very famous English mathematical physicist who moved to Princeton.
The fourth man of the Quantum Electrodynamics Prize. Well, although I'm not sure that he would like me to say that, actually. Right, but I mean, he was really one of my heroes, and so he invited me to give a talk at the Institute at Princeton on the date that I arrived in Princeton was in fact the anniversary of Einstein's birthday. It was a day that the US Post Office issued some stamps commemorating Einstein as a great American. I thought that was cheeky.
You're right. That's March 14th.
And the audience at the seminar in Princeton at the Institute consisted of a lot of people who were rather high-powered mathematicians who did what was called axiomatic quantum field theory, and they thought I must be wrong. But they were very well behaved and weren't rude about it. And at the end,
was the father of the atomic bomb, Robert Oppenheimer, in that audience? He was still alive.
He wasn't well. I didn't meet him. Okay. So he never he didn't appear at my talk, and I'm rather glad he wasn't there, given his reputation.
Yes, indeed. But Freeman was pleasant, was he?
Well, Freeman Dyson gave the first talk in the program of the afternoon on the stability of matter, which was quite intimidating for me because it was really high-powered stuff.
Yours wasn't high-powered stuff.
Mine was low level from the point of view of a mathematician. But apparently, I got the message across to the axiomatic field theorists that there was a problem for them. They couldn't see anything wrong with what I'd done. Oh. But I followed that up with a talk the next day, the next afternoon, in Harvard.
Yes.
And that was a very different experience. It was a dialogue between me and an assortment of opinionated people in the audience.
Right. Yes, I can imagine. All right. Well, okay. Just to I want to make sure there's room for questions. I just wanted to say, Peter there talked about the intimidating experience of going to see Freeman Dyson at the Institute of Advanced Study. By some sort of coincidence, I was there when we saw on the International Connection the announcement of what turned out to be the discovery of the particle. So let's have a look at Peter's, not the most demonstrative of people, but we can now see Peter's reaction. We now know that he knew a bit beforehand, but what happened when it finally went public. So could we have that sequence? You might want to turn around now, Peter.
Peter.
Yeah, but I didn't want to see them.
It seems yes.
You start, sir?
Together.
We are running out of time, gentlemen.
Well, of course, I am only extraordinarily impressed by what you have done, that we have somehow
started the whole thing, in a sense, is, of course, a great pride of us. But really, in part, what you have done, I am just amazed.
Well, I would like to add my congratulations to everybody involved in this tremendous achievement. For me, it's really an incredible thing that it's happened in my lifetime. It's taken...
It's a wonderful video. That so happy that it all came to such a fruition. All right, I suggest we take some questions from the audience, if we can. The lights won't be able to see very easily. Anyone's got any questions they'd like to ask Peter? I have a question here. This gentleman here. Please be ready with more questions. Sir. Oh, is there a mic coming? Yeah.
Coming. Peter, is it on? Yeah. Peter, it's a pleasure to be here and to listen to you. I'd like you just to give us a view on the importance of international collaboration in the context of the work that you've done and in the context of the future of science.
Topical question, Peter. Your views on the importance of international collaboration in science and the outlook for the future.
Well, it's
for a long haul tonight, ladies and gentlemen.
International collaboration, certainly in most areas of science now, is vital. The situation with particle physics at CERN is not the situation is maybe not so tricky as the situation with regard to some other issues in international science, but because the UK's membership of CERN is not the same thing. It's not intricately linked with the UK's membership of the European Union. But on the other hand, it's very obvious that the way that the funding of science is done now. In the UK and Europe, we are very considerably embedded in Europe, and to disrupt that is going to be produce a very difficult situation for British science. And well, that sort of issue is only one of many that the people who are attempting to negotiate Brexit are going to have to face.
We better leave it there, otherwise we will go on.
We won't pursue that one, I think.
It's a very, very good question, very important question. So, next one. I'm sorry, I'm giving favouritism to people at the front here, but this gentleman here.
Thank you, Peter, for coming to talk to us. Absolutely fascinating stuff. Can you say whether the Higgs boson... I'm sorry, thank you. Can you say whether the Higgs boson exhibits quantum mechanical behavior itself? And also, does the Higgs field show any signs of... Are there any distortions possible in the Higgs field?
I didn't catch that last bit, sorry. The last part of your question.
Yeah, in the Higgs field, are there any distortions of the field in the same way as we can get distortions in space-time? Mm-hmm. Can the Higgs field exhibit distortions itself? So there are kind of two parts to that question.
I picked up some of that. It was about the possible distortion of the Higgs field.
Yes.
Well, the distortion of the Higgs field treated quantum mechanically is what the so-called Higgs boson is about.
Yep.
I mean, it's the background field as a uniform constant field pervading the whole universe, which is responsible for changing the attributes of all the elementary particles and providing masses through the interaction of the Higgs field with everything else. And if you make waves on that background, and that needs to be possible for the theory to be consistent, it's like making waves on everything else. I mean, the simple statement about it is you go back to the work of Uncle Albert, the work for which he got his Nobel Prize primarily, which was actually the beginnings of quantum theory, where he pointed out that electromagnetic waves, in knocking electrons out of metals, were behaving as if they were a stream of particles, what we now call photons. That was the beginning of the ideas of quantum mechanics in a very qualitative way. Richard Feynman used to describe quantum mechanics as being, it comes in lumps. And what comes in lumps are all sorts of things which we were brought up to believe could be continuous quantities in terms of their values, energy, momentum, angular momentum, etc., attributes of dynamical systems. So, I mean, if you make waves on the background field, as you must be able to, as I said, then that's what the people at CERN eventually got to measure as so-called Higgs bosons.
Okay. It's just worth saying, just as a matter of perspective, that of course what's in these papers and the papers of Orgler and Brew, it's very subtle stuff. But fundamentally, I think it is an amazing thought, right, of what human beings can do now, right? What was suggested in this work is that the entire universe is pervaded by a field, just conjured out of nowhere, and that if you disturb that field, as Peter has said, you could produce a particle. And that idea came from that head.
Well, I don't agree with that, actually, because the idea was already implicit in the papers of Nambu and Goldstone, that sort of background.
But not the Higgs field, though, surely.
Well, yes. I mean, Goldstone had it already in his paper of 1961, but the missing ingredient, which was what I realized was necessary, was to combine that sort of theory of so-called spontaneous symmetry breaking, Nambu and Goldstone, which implies that the so-called vacuum is not as empty as you think it is. It has that some sort of background in it. I mean, the only difference from what Goldstone had, as what Frank Close calls Goldstone's other boson, is that now the parts of what Goldstone would have as a multiplet, symmetry multiplet of particles, the remainder of which have no mass, that problem has gone away, and they're providing the part of the description of the carriers of the force, the weak force, and so on. Mm-hmm. But Goldstone and Nambu implicitly have that sort of background already in their work.
Mm-hmm. Mm-hmm. Well, it's interesting perspective. What a great physicist Nambu was as well. You constantly mentioned that. It's barely known outside the particle community. Let us... please. Question.
I am no scientist, but I have followed everything that you have said, and understood it very clearly, because both you gentlemen are such wonderful storytellers. And what you've told us is a story of perseverance and patience. And there are many who say that our younger generation today have no patience. And there are plenty of young scientists in this audience tonight who I hope will disagree with that. But my question is, what advice would you give to our young scientists in the room here tonight?
Peter, you could be a sage. What is your advice to young scientists, having your many years of experience and having had such success? What would be your...
Well, given the way that science has developed in my lifetime, I think my principal advice is that when you pick the kind of course to take in a university with a scientific career in mind, make sure it gives you flexibility, because what we've seen, it's not so much in particle physics, but let's take things like molecular biology, is that there's a sort of coming together of scientific disciplines which were formerly distinct, and it's a question of having the right skills acquired mainly as a student to be able to move when you're motivated to do so into a field where you can do something. So keep your flexibility if you can.
Were you referring there to a point that, I forget the scientist, maybe someone in the audience can help me out here, but that Martin Rees often talks about, that you've got to be able to tackle problems that are soluble in some sense. Is that what you're referring to or not? Picking a problem that you can tackle in some way, is amenable to through your intellectual ability.
Yes, well, I had in mind, well, my experience as a student, a graduate student at King's College, was of being on the same corridor as the people who did the experimental work, which underlay the identification of the structure of DNA, and began the science of molecular biology. Well, at this time, it was a generation of people with a background in physics who were applying skills and technology which had been developed in wartime to solve problems in basic biology, which had previously been just, not possible to tackle. So I think that's a sort of sense in which I mean it on the hardware side, because it was the physicists who knew the technical developments of wartime who moved into biology. But it's true on the software side too, I think.
Mm-hmm. Okay. Very good. Thank you for asking that.
We have time for one more question,
One more
Graham.
question. Thank you. Yeah. One last question. Wait, sorry. If there's one there, please just go. I can't quite identify. I'm sorry.
All right. How can
we need a microphone? Sorry.
Yeah. How can a photon remain massless in a Higgs field?
How can a photon remain massless in a Higgs field? How can a photon remain massless in a Higgs field? It's a nice non-technical question for you.
By not interacting with it.
There we are.
There was something. Let me amplify that a little bit. I wrote down a very simple model when I wrote those papers. The people working in Brussels really did a bigger job, because they wrote down what would be the effect of spontaneous symmetry breaking in the fields which are the source of the force carrying fields. They wrote it down in very general form, and if you look at what that formula says, and you understand something about symmetries, you see that the what's now called the Higgs fields, if you look at the, as it were, the other side of the equations, is selective for reasons associated with the kind of symmetry you're breaking, and there are things amongst the components of the force-carrying fields which do not couple to the Higgs field, and those are the ones which stay massless, which carry long-range forces.
Good. There we are. There's your full explanation. Very good. Well, thank you for that, Peter. I think we're going to wind up now. I know Linda wants to say a few words. I just wanted to thank the audience for your attention, your perceptive questions. It's been a great pleasure talking with you now. I'm so glad we managed to lure Peter from his lair in Edinburgh. He did confide in me on the way. He's actually got to make a dash for it, because he doesn't actually use email, so don't try and email him, but he does have printouts. And he told me that one among his recent batch was an email from the Donald Trump campaign asking him if he'd be prepared to knock on doors to draw out the vote. And I've actually been told, that there's a Learjet waiting outside to take you to America, Peter. So we better hurry up. So, Linda, would you like to say your words? But thank you very much, Peter.